Hi everyone, so in this video we are going to be talking about polynomial functions and later rational functions. So polynomial functions are functions that have terms with whole numbered positive exponents. So for example, we have four different polynomials here. The first two should look really familiar. The first one is that of a line, the second is that of a parabola. So those we've actually explored before. Polynomials, though, don't have to stop at x squared. For example, we have one with x to the fourth and one with x to the fifth right here. And those graphs are shown below. Now, for this class, we aren't going to completely be graphing polynomials. However, we are going to at least get some basic ideas about the graph, some basic features about polynomials in general. So, first off, we're going to talk about degree. So, all of the ones that we've seen so far have been in standard form, meaning they're all multiplied out, there's no parentheses. A polynomial in standard form has a degree that is equal to its greatest exponent. So if we want to find the degree of each of these polynomials, all we have to do is look for the highest exponent. So for example 1, the highest exponent is 6. So the degree is 6. For example 2, the highest exponent is just x, which would be x to the first, so the degree is 1. Third example, there's only one term, so that's the highest, so it would be 3. And then for example 4, don't be fooled because they're not in order. The degree is always just the highest one, so this one would be degree 5. Now, it's a little trickier if they are not all multiplied out and in standard form. The degree of a polynomial in factored form is equal to the sum of the exponents on each factor. All right, so for example 5, what we're going to do is we're going to look at each factor, which we have 2. Each of those is a factor. And we're going to see the degrees on them. So we have degree 2, and then if there's nothing there, it's degree 1. So, or sorry, not degree 1, but rather the exponent is 1. So for the degree, we add those two exponents, and we get that it's degree 3. Same thing for example 6. We have 3 different factors. So we're going to look at the exponents on each. Again, for the x, there's a hidden 1 there. Then there's a 2 and a 3. So if we add all of those, we get that it's degree 6. For 7, we have a 2, a 1, and a 1. So that's degree 4. And for 8, we have a 3 and a 4. I'm not counting this 2 because there's no x with that 2. If there is an x with it, we do have to count that exponent. But if there's no x, we're just going to ignore that 2 out front for degree purposes. So if we add up the 3 and the 4, we get that it's degree 7. All right, next up, we're going to talk about end behavior. So polynomial functions of an even degree have graphs that rise or fall on each end. They do the same thing on each end. as in they're either both rising or they're both falling. Polynomial functions of an odd degree have graphs that rise or fall on opposite ends, meaning that if it goes down to the left, it would be going up to the right. If it was going up to the left, it'd be going down to the right. They do the opposite on each end. So for example, for part A, we have x squared and x to the fourth both graphed. If you notice, both of those have an even degree, and on both ends, they are going up. For part B, x cubed and x to the fifth, for that one, if you notice, it's going down to the left and up to the right. That's because both of those have an odd degree, so if one side is falling, the other side should be rising. If we look at the graph of negative x cubed, so if x cubed looks like this, because graphed right there, then negative x cubed just means it'd be flipped upside down, so it's going to look something like that. Alright, so this one, again, it's cubed, so we know that they should be going towards opposite directions. So the left is rising, the right is falling. But also notice that since we had that negative, the right side is now falling. For parts A and B, all of those were positive, and if you notice, it was rising to the right on both of those. A negative just means that the right side is going to be falling no matter what. All right, so D, what would the graph of negative x to the fourth look like? Well, if x to the fourth looks like this that we have graphed, then negative x to the fourth, again, would be upside down. It would look something like that, which again makes sense because it's falling to the right, because it's negative, and it's fourth degree, which is even, so both of the sides are doing the same thing. They're both falling. Last thing we're going to talk about is intercepts for polynomials, and specifically we just want to talk about the maximum number of intercepts that a polynomial can have. So the number of intercepts is always going to be equal, the maximum number of intercepts is always going to be equal to the degree of the polynomial. Right? Now I say the maximum number because it may actually have less. Like for example, you can definitely have a parabola that is somewhere up here, and that has no intercepts. But you can also have a parabola with one intercept if it just touches the axis and turns around. Or you can have a parabola with two intercepts. Let's say something like this would have two intercepts. A parabola is based on x squared, so the squared meant it could have a maximum of two intercepts. Right? Again, it doesn't guarantee that there's going to be two, but it does say that there's going to be a maximum of two. There can't be three intercepts for a parabola like this. All right, so the last example then, what is the maximum number of intercepts that a polynomial of degree 12 could have? Well, the maximum number of intercepts is just equal to the degree. So if it's degree 12, then the answer is just 12. All right, that's where we'll leave off this video. In the next video, we're going to start talking about rational functions. So I will see you in part 2.